All right, so we're going to talk about the Bronsted-Lowry theory of acids and bases. Yes. Lowry. You don't like when I spelled it? There is a slash through Bronsted's name.
Or is that how you write your O's?
No, that is the guy's name.
It's legit.
It is legit. That's right. He's Danish. And that's one of the letters you use in the Danish language, along with Russian and some other languages. Okay? Bronsted-Lowry. Now, Bronsted-Lowry's, huh? Slash here and a dash here, but this is not, the reason the dash is here because it's two different people.
Why doesn't Lowry have a slash through his O's?
Because he's not Danish. He's British.
Oh my gosh, that's really
All right, pay attention up here. Let's not worry about whether we got slashes and dashes. Pay attention on the acid and base. Okay? Now, listen please. Now, Bronsted-Lowry said, listen, Bronsted and Lowry these two guys came up with this idea that Arrhenius was an insufficient definition for some things. Okay? Example, we know that ammonia, when we dissolve it in water, behaves just like a base. Okay? We know that ammonia, when you dissolve it in water, behaves just like a base. That's what you use to clean your floors with at home, or sometimes your kitchen counters. All right? Whatever. I'm just listen to me. Okay? Pay attention. Don't get off subject here. Okay? All right. But there's no OH in here to donate. No hydroxide ions to donate anywhere. Therefore, they said that since this really is a base because it acts like a base, in a practical sense it behaves like a base, the Arrhenius definition isn't going to really work all the time. We want to come up with something a little better. Got that? All right. So, in their definition then, an acid is anything that donates a proton to something else. Okay? And what's a proton? Close. Hydrogen ion is a proton because to get a hydrogen ion, hydrogen atoms have protons and electrons. We get rid of the electrons, we got protons. Okay? But a base, yes, is anything that accepts a proton. Hello? Yes. I'll do that. All right. So a base is anything that accepts a proton. What? Yes. All right, now, let's look at this in the simplest possible way. Okay? So look at this in the simplest possible way. Let's look at our hydrochloric acid again. Okay? Let's look at our hydrochloric acid again. So in the Bronsted-Lowry theory, hydrochloric acid has to give away its proton to something else.
Oh, it's gas. I thought it was
hydrochloric acid has to give away that hydrogen ion or that proton to something else in order for it to be an acid. Well, most of the time in high school chemistry, we're working with acids that are in water, because we said so a while ago. Okay? So we're going to put it with water. Okay? And we're going to give away this hydrogen ion. We're going to take that hydrogen ion off of there. And we're going to put it on water. So what do we have left over here? Take the hydrogen ion off. What's left right here?
H3O. CO plus H3O.
Well, that's true, but I want the charges along with the Cl, because if we take a hydrogen ion that's positive off, what's this have to be?
Oh, Cl negative.
You have to have a Cl negative. And we saw a while ago that it's aqueous. Okay, that's aqueous. All right. And Evan, you're right. We put the hydrogen on there. We get what?
H3O.
And it has to have positive charge, because that has a positive charge. This is neutral. You're adding a positive charge to a neutral. You've got to have a positive. Okay? And that's the way you think about Bronsted-Lowry acids working. Good question. What a good question.
It's
Hydronium.
Hydronium. What? Since we watched that video? Oh.
All right. So we said then that this is an acid because it donated a proton to something else. In this case, it donated to water. What was a base? Scratch your beard, scratch your head. What's a base? Think.
Well, the water was the base.
There you go. Why is it a base?
Because the other one was an acid, so
the HCl was an acid, and water can be a base or an acid.
Okay, but use this definition right here. You're right. Everybody's right so far. Good.
Because the acid has to donate to something. So
Water accepted the proton, H plus. That's why it's base.
This is our proton, and the proton went to water. Water met the definition of Bronsted-Lowry's base. It accepted a proton, so this is a base.
yeah.
All right? Now, when you pull a hydrogen off of a substance so that it can donate that proton to something else, what do you have left when you remove that hydrogen ion? Is a base itself. But it's a special, we call this the conjugate base of this acid. It is a base, because guess what? This can accept that hydrogen ion and make HCl all over again. Okay? And this hydronium, it can give away the hydrogen ion to something. So it's an acid. This is the conjugate acid of this base.
And around and around it goes.
Yep.
Why did the videos you brought up here?
Oh, go back and watch it again.
I know the reason to it, but why would you use that?
Why not?
Metaphor.
Why do I use it? Why do I talk about different metaphors? Who cares? It's just a way of talking about it and thinking about it. All right.
Hey man, you're getting rough.
Shut up, stop saying it.
All right. Now, so in the Arrhenius definitions of acids and bases, it's the hydrogen ion that does the work of an acid. Okay? In the Arrhenius definition of acids and bases, the hydrogen ion does the work of an acid. Okay? So it's a hydrogen ion that's giving you that sour taste. It's a hydrogen ion that's actually neutralizing the base. All the things that acids do, the hydrogen ion is what does it. Okay? And the hydroxide ion does the work of a base. Okay? It's what makes your skin feel slippery when you get it on your hands. One of the physical manifestations of a base is that it makes your fingers feel slippery.
So is it in lotion?
No, that's slippery for a different reason. The reason that bases feel slippery on your hands is that it dissolves your skin cells. It makes it kind of a mush that feels slippery. Okay? In a Bronsted-Lowry acid, it's the hydronium that does the work of an acid. Okay, so let's take a look at what we do with this when we put it with the base. Remember, the base actually broke up in water. It broke up into potassium and hydroxide, KOH, a solid. Put it in water, it dissolves into potassium ions and hydroxide ions. Okay, so let's put that together. K plus hydroxide plus our acid stuff here from the acid base. The reaction when you put the hydrochloric acid in water, you get this stuff. Let's put it with this. Plus this, because all of that's in the water. We dissolved all this stuff, so this is all in the water. And let's see what we get on the other side of the equation when we put all this together. So we're using Bronsted-Lowry theory now to talk about what the acids and bases did in our neutralization experiment yesterday. Okay? Only we're going to use a little more complex but more complete definitions of acids and bases to do it. So what do you think you're going to get on the other side?
Would you have to put the positive and negatives together? Or would you put the positives together and then put the negatives?
No, the positives have to join up with the negatives.
Okay.
For every positive, you need a negative somewhere. Now, that doesn't always work out that way, but that's more complex chemistry for another time.
Are we still giving up protons?
I don't know. Can we give up protons using this stuff?
We got one, I think.
Okay. Where?
Got that case.
Well, but that's not a proton. Proton is just a hydrogen ion. Because potassium, remember, has multiple protons and multiple electrons.
Right.
So if we give up just one electron to make a potassium ion, we still got all those other electrons and a whole bunch of protons.
Right.
Okay? So, what kind of things should happen here? What could we get out of this stuff? Okay, if you put those together, what's going to happen? Okay, well, let's take a look at it. Let's pull it down here and do it a little separately, okay? H3O. Just look at those alone, plus the OH. Okay? Using Bronsted-Lowry, donating and accepting protons, what can happen here? Using Bronsted-Lowry, what can happen here?
You can give up the H to the OH.
So the H plus here, he says, he's proposing the H plus here can go over here and join up with that. Alright, if we do that, what are we getting on the other side of the equation then?
You're going to get 3O. Right? Well,
we're going to take the H plus off of this. Okay? Pay attention up here, guys. We're going to take the H plus off of this. What's going to be left?
No.
H2O. What happens when I put the H plus on this? Did we neutralize the acid?
Yes.
Duh. Yeah. Okay. Turns out that's the net ionic equation when we get done with it. Okay, because what's happening is this is joining up with that, so that we're going to, well, let's put down potassium because it's not going to do anything. It's going to be a spectator. Then the OH is joining up with this, and we get actually 2 H2Os here. Right? 2 H2Os. And the chloride's all by itself. Alright? And when we get rid of all our spectator ions, this is what we get. Well, we're moving a lot of ions around, aren't we? Man, we're tying in all this stuff we've learned all semester long. Right? From Unit 2. From Unit 2, we learned about the structure of the atom. Electrons and protons. Well, here's our electrons and protons, the structure of hydrogen, making a hydrogen ion, which is a proton. That's Unit 2. Very beginning of the semester, right? Balancing equations. Okay? Well, actually, there is more than one way to balance an equation. What we're looking at here is, well, what is the equation actually telling us when we use it this way? When we first learned, I guess it was Unit 5 when we learned about net ionic equations. Net ionic equations then help us to understand all this acid-base theory. Because without net ionic equations, none of this makes any sense. And that's why we need to understand net ionic equations when we're learning about equations. And now we're using them in a way that's actually practical for us. Okay? Yes?
Why don't we combine the H2O on the right side?
Over here?
Come together.
I could.
But
I did here.
like you wouldn't do like H or
No, because the molecule is H2O. We can have 2 H2Os, but we can't have H4O2. That doesn't exist. Okay? But that goes back to Unit 3 where we learned Unit 3 where we learned about putting together atoms to make molecules. Okay, remember when we did Lewis dots and all that? Sharing electrons. Remember hydrogen ions had 1 electron. Oxygen had 6. Right? Yeah, and we shared the electrons to make our water molecule. Well, let's look at that for a minute because that's a really interesting idea. How about this H3O? How do we do this for H3O? We got not just 2 hydrogen atoms and an oxygen. We also got a hydrogen ion to put together to make that H3O. See what we're doing here? We're moving the hydrogen ion on the H2O. How would that go together? Build a Lewis dot formula for the combination of these things. Do that now. Right here.
I can't see that.
Oh, sorry. Right here. Build a molecular formula for this. Now this is actually going to stretch a little bit. We haven't actually covered part of this yet. See if you can figure it out. If we put water together like this, how do you put all those together? Well, that's a deep subject with a lot of water. Wells. Let's plan on doing our next lab on Thursday. Oh, today's Wednesday. No, let's do it Friday. I think we need another day. Okay. Let's do the next lab on Friday. Okay. I will give you. Wait a minute. Let me think about that. Yes. No, we need a little more theory time, I think. I hate to do a lab on Monday, but let's plan the lab on Monday. Okay? And I will give you procedures and hazards to do for this. Okay? All right. Who's got it? Who's put this together?
Not me.
Well, what are you waiting on?
I got it.
Okay. Well, we know that these two can share here, right?
Yeah. I got it.
What about this over here? Huh? It doesn't. This is a hydrogen ion. It lost its dot. Remember, with hydrogen ions, we got one because we got rid of its electron. So, huh?
So we stick it to the side.
Stick it to where?
To the side
How about that? Man, this guy's a genius today. He just kind of goes over here and joins up with one of these pairs of electrons. Because it wants a pair of electrons, doesn't it? That's the whole idea. That's that. You know. We call it the octet rule, but for hydrogens, it's more like the duet rule. Okay? So then we get this, and this, and this, and this hydrogen ion joins up right there, but it's still going to make it a positive thing overall. So I'm going to put a bracket around it to show this positive charge is shared for the whole thing.
beautiful arrow.
You like that?
Very artistic. I said artistic.
He said artistic. Golly.
No, we're not talking about cheese sticks.
Cheese sticks.
I said cheese sticks.
All right. Okay. Got it? So if I put a water molecule with a hydrogen ion, this is like the Arrhenius theory right here, donating a hydrogen ion to water, right? But then if I put the Arrhenius theory, kind of put it into what we're doing here with Lewis theory, I get Bronsted-Lowry. There's the Bronsted-Lowry theory of what an acid is. Got that? Is that a little too much for you all at one time? All right. Arrhenius theory says anything that donates a hydrogen ion to water is an acid. Well, there's our hydrogen ion. Bronsted-Lowry says anything that donates a proton to something else, well, there's our water molecule written in the Lewis form. Remember Lewis dots? We just donated that onto Lewis, and we get the Arrhenius acid, H3O+. I'm sorry, not the Arrhenius acid, but the Bronsted-Lowry acid. Okay? Now, this is important, guys. This is really important. You've got to be able to recognize what the acid is, what the base is, what the conjugate base is, and what the conjugate acid is. And it's not always these same things. Okay? Got that much? Huh? Yes or no? You have a question? Yes. Because that's the way you spell his name. All right, let me back up just a second here and let's be clear. When you break up something like this is the dissociation equation. Okay? What does associate mean?
Put yourself with, like,
Combine. Join up together. Okay? Hang around together, right? Well, this is also a dissociation equation. It's just kind of modified for Bronsted-Lowry, okay? Here I'm asking you to do the Bronsted-Lowry dissociation equation for acetic acid in water, okay? So we'll get that written down, and I'll kind of go back and explain generally, in a general sort of way, what we're talking about here, just to make sure we're clear about the terminology. Everybody got it written down?
No.
Didn't I tell you to stop saying no? I'm just joking now. Just joking now. Now that's an acceptable no. Yeah. And honestly, that's just an honest response, because a lot of people are saying no in their head without speaking out. Okay, so in fairness to Evan, he's got the guts to say so. Now listen, I can deal with this. I can deal with the saying no out loud better than I can deal with a no in your head. Because if you say no in your head, I can't help you with that. You got to come up. You got to figure it out. I can do it. Hello. I'll do that. Sure. All right. So you need to go to the attendant's office. Get that. Wait a minute. Is it you? No, Gillespie. I'm sorry. What? All right. Now listen up, guys. Guys, it's a little early to put stuff up. I was going to take a minute or two and kind of make sure we're clear on the terminology here. Now look. Anybody still writing? Alex, do this first because I got to talk about something else. All right, now, the dissociation equation. that is like, but not the same as, because we're talking about a different acid. This is the dissociation equation. Got it? All right. The neutralization equation. This is our neutralization equation here. We neutralize the acid we get with the hydroxide. Okay. The protons moving around. That's what I did here and here. And the net ionic equation for number 2, well, that actually, the net ionic equation for our example was this right here. Ooh, and I forgot one more thing. What? Yeah. You know how it is with white people. They all look alike.
I'm offended.
You should be offended. Y'all know I'm joking. Come on. I'm a white guy. I can tell the white people apart. Come on.